Good evening, class. Welcome back to Living Systems 1. We are now in week 3 of semester. As I've said before, semester goes very quickly. So really important to keep on top of everything, particularly if you are a full-time student. So tonight's lecture is about ionic compounds. So you remember last week we looked at elements in particular, elements on the periodic table and how the periodic table works in terms of some of the features, some of the trends that we can see on the periodic table. But the reality is that many of those elements don't exist in nature as individual atoms. More often than not, they tend to actually join with one or more atoms of either the same element or different elements to form compounds. So that's what we're going to be talking about tonight. All right, so we just thought about that concept of joining two or more atoms together, and that joining is referred to as bonding. There's lots of different types of bonding that exist in the world of chemistry, but we will be looking tonight at one major type of bonding and next week at the other major type of bonding. So bonding is simply the joining of two atoms in a stable arrangement. So this suggests that the bonding of the two atoms results in a more stable configuration than the configuration of the atoms on their own, and that's certainly the case, and we'll see to a certain extent why that is a little bit later in this lecture. So elements, of course, when we're talking about the chemistry of atoms, of any elements, that chemistry, or in other words, the reactivity of the atoms is really determined by the electrons. And elements, as you'll see, will tend to gain, lose, or share electrons to attain that stable configuration. So here are the two major types of bonding. As I said, there's lots of others. This is the one we'll concentrate on tonight, ionic bonds. And ionic bonds result from the transfer of electrons from one element to another. So an atom of one element, for example, will give up one or more of its electrons. Of course, here we talk about valence electrons, which we learned about last week. And the atom of the other element will receive those electrons. Okay, so that's ionic bonding. Covalent bonding results from the sharing of electrons between two atoms rather than gain or loss of electrons. And we'll go into more detail next week. All right, so ionic bonds tend to form mostly between a metal on the left side of the periodic table, more specifically to the left of the metalloids, and a non-metal on the right of the periodic table. So you'll note that with quite a few of the tutorial questions, you really need to be able to identify the compound as being an ionic compound. So when you're doing this, make sure you keep this in mind. Okay, look at the compound. Does it consist of a metal and a non-metal? Or does it, for example, just consist of two non-metals, in which case, most likely it's not an ionic compound. All right, let's have a look at a great example of an ionic compound, which is here. So this is sodium chloride, which you might know by now is just our common table salt. So one sodium and one chlorine here, which is referred to as chloride, and you'll see why that's the case also later on. All right, so if we take one sodium is a metal on the left side of the periodic table, and we take chlorine is a non-metal on the right side of the periodic table. Those two elements will react to form sodium chloride. But the important part of this slide really relates what's happened to the sodium atom. And we can see here that it's picked up a single positive charge. Hence, it's written here as sodium Na+. Okay, it is now charged. It is an ion. What's happened to the chlorine? The chlorine has picked up a single negative charge, as you can see there. So why is it that the sodium has become charged and the chlorine has become charged? That's the question that we're hoping to answer. All right, so ions are charged atoms or charged species in which the number of protons and electrons in that atom is unequal, or it could be the number of protons and electrons in an entire molecule that's unequal, but we'll worry about that bit later. All right, so let's just illustrate this because this is a really important concept here. And it's sometimes a little bit confusing for students. So I'm going to draw here, some protons. This is my hypothetical atom. And it has 4 protons. So you know each one carries a positive charge. And of course, in the neutral state of this atom, it also has 4 electrons, so they're balanced. So what is the overall charge on my hypothetical atom? Of course, the overall charge is 0, or we can just say neutral. Okay, that's pretty straightforward. But what happens, let's look at this example again. So we've got a plus, there we go. Okay, there's our 4 protons. Now, what happens if this hypothetical atom loses an electron? What happens if it loses an electron? Obviously, now we can see that 1 proton is not balanced. Yeah, it's not balanced by a negative charge. So what would be the overall charge on this atom now? Overall charge. Who wants to hazard a guess here? Overall charge, if you've got 1 plus 1, correct?
It's positive.
Yeah, it's a positive charge, plus 1. I mean, that's often written just as a single positive without the 1, but let's just write plus 1, okay? Now, let's try that again. Let's go again. And this time, my atom has lost 2 electrons. What's the charge on this now?
+2.
+2, correct. It is now a +2. +2 charge because you've got 2 protons here that are not balanced by those negative electrons. Correct. Okay, let's go again. Now this time, we are gaining an electron. Gaining 1 electron. What is the charge on my atom now? Because now we have an electron, negative electron. It's not balanced by a positively charged proton. Correct, -1 charge. Good, everyone seems to be getting the hang of this. And same thing again, but this time we're going to gain 2 electrons. Gaining 2 electrons. Oh, and I'm getting very, very lazy here now with my drawing, as you can see. Gaining 2 electrons, correct. Good, -2. Okay, wonderful. All right, now let's relate that to sodium. So we saw that sodium had a single positive charge. Yep, on the previous slide, and we saw that chlorine had a single negative charge, which I'm going to draw here to the left just to illustrate a point. Okay, positive and negative. What do you think will happen between a positive and a negative charge? Would there be attract? Correct. There will be an attraction. Yep. Opposite charges attract. Okay, so there is the attraction between them, and this is referred to as an ionic bond that forms between those two atoms. And that's written here for you, ionic compounds. So for example, sodium chloride. Yeah. This is an ionic compound, consists of oppositely charged ions that have a strong electrostatic attraction for each other. Okay, so I think that's fairly straightforward for everyone. There are two types of ions. Our positively charged ions are called cations. So sodium is a good example, and the negatively charged ions are called anions, like chloride. All right, let's clear all that and move on. All right, so our cations are positively charged. A cation has fewer electrons than it does protons. And we've got a great example here. Once again, sodium. So if you look up sodium on the periodic table, you will find that it has the atomic number 11. What does that immediately tell us about sodium? What does that tell us about sodium? That number 11. Atomic number, yes, very good. So that means that a neutral atom of sodium has 11 protons, correct? And if it's neutral, we then can infer from that that it also has 11 electrons. That's exactly what we see here. 11 positive protons, 11 negative electrons. Now, let's take a look down here at the electron configuration. Can someone tell me the number of the valence shell? Oh, someone's already one step ahead of me. Yes, it has one valence electron, and the valence shell, of course, is shell number 3. And there's the valence electron, one valence electron. This is not stable. To have one electron, or usually, it's not stable to have one electron in the valence shell. So sodium has this great tendency to lose that electron. It tends to lose that electron so that it results in this. It still has 11 protons, but it now has only 10 electrons, and hence it becomes charged. So here we have the sodium cation, but more importantly is the new electron configuration, which results from that loss of one electron. Now we can see that the valence shell is shell number 2. How many valence electrons do we have? 6 here, 2 here, 8 electrons in total in the outer shell. That number 8 seems to be a particularly stable electron configuration for many of the elements. Not all of them, but for many of them. In other words, now sodium has a completely filled valence shell. Very stable for sodium. Okay, let me just clear this. All right, let's move on to our next example. And this example, we have magnesium. Okay, let me just get my pen again. All right, we have magnesium. If you look up magnesium on your periodic table, which is very useful to have close by, you'll find that it has this atomic number, which tells us immediately that an atom of magnesium has 12 protons. In a neutral atom of magnesium, there will also be 12 balancing negatively charged electrons. All right, so here's the electron configuration for magnesium. 1s2, 2s2, 2p6, and here's the valence shell. 2 electrons in the outer shell. Once again, not particularly stable, this configuration for magnesium. So magnesium has this tendency to lose those 2 valence electrons. The end result is that it still has its 12 protons, but now it only has 10 electrons. So because 2 protons are no longer balanced with negative electrons, the magnesium picks up a 2+ charge to form the magnesium cation. Let's look at the resulting electron configuration. And you can see once again, the new valence shell is shell number 2, and there are 8 electrons, a lot more stable for magnesium. Let's clear that and move on to our next example. All right, now we'll look at anions, which are negatively charged ions. And an anion has more electrons than it does protons. The example here is chlorine. Chlorine number 17, atomic number 17, which means that it has 17 protons. In a neutral atom of chlorine, it will also have 17 balancing negatively charged electrons. Let's look at the electron configuration. Valence shell number is shell number 3, and we have 7 electrons in this shell. Now, for chlorine, the opposite applies. Rather than getting rid of valence electrons, so rather than losing valence electrons, chlorine tends to be that type of element that gains electrons. It will scavenge electrons very strongly from other elements that are more likely to lose their electrons. So when chlorine gains 1 electron, let's look at the result. So once again, still has its 17 protons, but now it has 18 electrons, so 1 additional electron, and this confers, as we can see here, a negative charge. And we have formed now the chloride anion. Once again, formation of an anion has meant that we now have 8 electrons in the outer shell. And once again, that is quite a stable configuration for chlorine. All right, so by gaining 1, 2, or 3 electrons, an atom will form an anion with a completely filled outer shell, or sometimes completely filled subshells within a shell of valence electrons. And this brings us to this general rule that we can use. It's called the octet rule. This applies to main group elements. So can anyone remember what we mean by the main group elements? Does anyone remember this? Which elements are the main group elements? So unfortunately, we can't apply all these rules to all the elements on the periodic table. There's always exceptions. So main group elements. Who remembers that? 1A to 8A, yes. So remember groups 1A through to 8A, which means the first 2 groups on the left side of the periodic table, and then on the right side, groups 3A through to 8A. They're all referred to as the main group elements. All right, so the octet rule means that a main group element is particularly stable when it possesses an octet of electrons in its outer shell, where an octet equals 8 valence electrons. All right, we can relate the group number that the element is situated in to the ionic charge that that particular element forms for the main group elements. Okay, so this is a good tip to remember. So elements in the same group tend to form ions of the same charge. and we'll see that in just a minute. Metals tend to form cations, and for those metals in groups 1A, 2A and 3A, the group number, that is 1A, 2A or 3A, equals the charge on the cation. In other words, elements in group 1A tend to form a +1 charge. Elements in group 2A on the periodic table tend to form a +2 charge, and so on. So the non-metals tend to form those negatively charged ions called anions. Okay, different rule applies here. So for the non-metals in groups 6A and 7A, which tends to be the ones that we deal with the most, the anion charge that forms on a particular element simply equals 8 minus the group number. In other words, 8 take away 6 or 8 take away 7. And we'll see some examples in just a minute. All right, so let's start with elements in groups 1A to 3A and look at how these group numbers relate to ionic charge. So remember, the charge on the cation for these elements equals the group number. So group 1A metals, and hence we're using the letter M here. These have 1 valence electron. We know that because they're found in group 1A, and here's the single valence electron here. So these elements tend to lose an electron to form a single positively charged cation. Just note here how the loss of an electron is actually written here as plus an electron. But because this is written to the right side of this reaction arrow here, it means loss of an electron. I know, a little bit counterintuitive, but that's how it works. All right, so what about group 2A elements? So belonging to group 2A means that they tend to have 2 valence electrons. So we're still talking about metals. These 2 dots, as you know, indicate the 2 valence electrons. These elements, or rather the atoms of these elements, tend to lose those 2 valence electrons. We can see that indicated here where it says +2 electrons. Written to the right side of this reaction arrow means a loss of 2 electrons, and as a result, this metal will pick up a 2+ charge. Group 3A elements have 3 valence electrons, and they tend to lose those 3 electrons to form a 3+ charge. All right, now let's look at the same thing but for anions. In particular, groups 6A and 7A, where the charge, the anion charge, equals 8, take away the group number. All right, group 6A elements, and the element itself is denoted by this X. Belonging to group 6A means they have 6 valence electrons, and we can see the valence electrons represented here as dots. Rather than losing those 6 valence electrons, they tend to scavenge electrons. So +2 electrons means that they gain electrons. Rather, the +2 electrons is written to the left side of this arrow. All right, so as a result, this group 6A element now has picked up a 2 negative charge because it has 2 additional electrons, remember, that are not balanced by 2 protons. So how do we know the charge? We simply say 8, take away the group number, which is 6A, and that leaves 2. So hence the 2 negative charge. Group 7A elements, very reactive halogens, as you know. They have 7 valence electrons. They want 8 valence electrons, so they tend to scavenge a single electron, and this confers a single negative charge on the ion. We know what that charge is because simply 8 take away 7 equals 1. All right, so they're good to keep in mind, and here is an excellent summary of everything that we've just discussed. All right, so we're just looking at some of the main group elements. All All right, we can see here group 1A. 1A, group 1A metals tend to form cations with a +1 charge. Good to see that many students in the last tutorial, all those that I've marked so far, remember that hydrogen is not considered to be a metal. It's the exception to this rule. All right, group 2A. Group 2A metals form cations with a 2+ charge, as you can see here. All right, moving over to 6A. 6A, group 6A non-metals form anions with a 2- charge, and the group 7A halogens form anions with a -1 charge, as you can see. So it's good to have a look at this table just to remind yourself of what the charges are on these elements, especially relating that to the group numbers. All right, then we come across other elements. So we're still looking at metals here, and they form cations, but the magnitude of the charge is harder to predict. So we can't just use the group number often to predict what the charge is. And often with elements, they'll form cations, for example, of different charges. And we can see just some simple examples here. So here, for example, Cu, so that's copper. And you can see that copper can form a single positive charge or a 2+ charge. Here's another good example, also relevant. Fe is iron, and iron commonly forms a 2+ or a 3+ charge. So this is not a comprehensive list of all the different ions that can be formed. These are just a few of the common ones. All right, this is a really important slide because it determines very much how we name certain ionic compounds. So those compounds that form ions with variable charges, we name quite differently to how we name our normal ionic compounds. All right, so keep slide 14 in mind because I'll be referring back to this slide. All right, so here we just have, just for your interest, some of the common ions in the human body, but also some very critical ions in plants as well. So we really should have an image here of a plant, but that's okay. All right, calcium. Calcium cation, Ca2+, found in teeth and bones. Yes, we're probably all aware of that. Is the calcium cation important in plants? Have a guess, yes or no? Is the calcium, so someone has said yes. What does everyone else think? Have a guess if you're not sure. Is the calcium cation, Ca2+, important in plants? Okay, we have a yes, we have a couple of no's, another no. Come on, everyone, have a go. We have a yes, a no, a no. Oh, I should have set up a poll. Another no. All right, so we've got a probably roughly equal number, maybe a few more no's than yeses. All right, I'll come back to that. What about this one? Sodium ion and potassium ion, found in all body fluids in higher animals, also found inside cells at different concentrations. What about in plants? Are sodium and potassium ions important in plants? All right, we have a yes, a yes. Yes, yes. Oh, everyone's going for yes now. That's interesting, isn't it? All right, a few yeses. All right, we'll come back to that one too. All right, what about this one? I hope you're not all doing the Google search. Add potassium to soil. Yeah, absolutely. Yeah, absolutely. All right, that one's probably more straightforward. What about this one? Iron, the iron cation, Fe2+. Everyone's probably aware that it's a critical component in hemoglobin found in red blood cells. And of course, it's critical because it binds oxygen, strongly binds oxygen and transports oxygen around. Is this important in plants? Okay, we have a no. We have a yes. So the ion, cation. All right, we've got some yeses. Yeses. Okay. All right, so mostly yeses for that one. What about this? Chloride. Negatively charged chlorine. We have a no. Present in the gastric juices of the stomach, yes. And also other fluids in the body of higher animals. So we've got quite a few no's for this one. Quite a few no's. All right. Interesting. And the last one, magnesium cation. Of course, very important for nerve transmission and muscle control. Is that important in plants? We've got some yeses. Got a few yeses there. All right, very interesting. Okay, great. All right. Now, let's look at some of these. Who's familiar with the concept of gas exchange in plants? In other words, well, everybody's familiar with the concept of gas exchange in relation to plants having an absolute requirement to take up carbon dioxide. Yeah, everyone's familiar with that? Yeah. Okay, everyone's familiar with that. How does the carbon dioxide get into the plant? This is the next question. How does the carbon dioxide get in? Through stomata. If you're not familiar with stomata, there's simply these tiny pores that are found predominantly on the surface of leaves. No, not stigmata. No, not stigmata. Stomata. Stomata. Yeah, that's very good. Did I say stigmata? So stomata. Tiny little pores. You can't see them unless you use a microscope, and then you can see them beautifully. Stomata, they're quite amazing. All right, so these little pores open and close depending on environmental conditions, and of course when they're open they allow carbon dioxide to diffuse into the air spaces within the leaf. And of course they enable, as some of you have just mentioned, they enable photosynthesis. Fantastic. Now, what if I told you that the opening and closing of the stomata is facilitated by those two ions, and this one too. Those ions are actually very important in facilitating the opening and closing of stomata to respond to environmental conditions. Obviously, if environmental conditions are good, then the stomata will open and allow the gases to diffuse in. And of course, someone said, I believe you. Don't believe everything that you're told. Unless it's someone that has researched something for many, many, many years and they are the expert. But anyway, so very important. Now, this one down here. Okay, so I think most students said yes, the magnesium ion is very important in plants or important in plants. Can anyone tell me the #1 critical function of magnesium in a plant? So yes, you're right. Those students that said yes, plants need magnesium, helps absorb nutrients, root growth. Yep, #1. I'm after that critical #1 function for magnesium. It's used in something. It's used in something to make something. To make something that's essential for the process of photosynthesis. Without it, photosynthesis would not. Chlorophyll pigments, correct. Yes, very good. Magnesium is at the center, is at the core of the chlorophyll pigments, yep, which enable the process of photosynthesis. All right, very good. All right, so just so plant students can appreciate, which I'm sure they already do, appreciate ions as much as students that are studying animals. All right, now let's look at a formula for an ionic compound. So once again, our classic sodium chloride as an example of an ionic compound, and you'll note that there are no charges indicated here. And that's because the sum of the charges in an ionic compound must be 0 overall. Let's look at how that works. We start off with a sodium ion and a chloride anion. Single positive charge, a single negative charge. That means we only need one of each to balance out the charges and therefore form this ionic compound, which has a 0 charge overall. Okay, so that's straightforward, one of each. So when you look at something like this, an ionic compound, you won't see the charges being indicated. The charges will not be indicated in the formula here for the ionic compound. You would just assume that in this compound, we have a sodium, a positive sodium, and a negatively charged chloride, okay, that are joined together, bonded together by an ionic bond. Let's look at another example. Now, balancing is important. Several of your tutorial questions will require you to look very carefully at the charges to enable the correct balancing to occur. All right, calcium cation. Calcium tends to form a 2+ charge. Fluorine, or rather fluoride, when it's charged, forms a single negative charge. So we couldn't take one fluoride and one calcium and expect the charges to be balanced. We need 2 of these fluoride anions for every 1 calcium. And that's exactly what we see in this formula for calcium fluoride. 1 calcium, 2 fluorides. So remember, when you see that number as a subscript, it indicates the number of atoms of that particular element. So example, 2 fluorides to form calcium fluoride. All right, so let's now look at how to write a formula for an ionic compound. I won't be asking you to do this, but it certainly helps just to look through these steps. Step 1, identify which element is the cation and which is the anion. So you'll be referring to some of the tables that we've already referred to in this lecture. When you're working through your tutorial questions, for some questions, you'll also be referring to the periodic table. All right, so remember this rule: metals tend to form cations, non-metals tend to form anions. All right, use the group number when it's a main group element. When it's a main group element, use the group number to determine the charge on the atom. So for example, we've got potassium here. It's a metal, so it's going to form a positive charge. It belongs to group 1A, so it'll form a single positive charge. Here's another metal, calcium. We've already talked about that. It's also a metal, belongs to group 2A, so it'll form a 2+ charge. What about the non-metals? Group A element, chlorine. So being a non-metal, it'll form a negative charge. And another non-metal here, oxygen, belongs to group 6A. Also remember the rule, 8 take away the group number. 8 take away 6 is 2, so it forms a 2 negative charge. All right, determine how many of each ion type is needed for an overall charge of 0 in the final compound that's formed. All right, so once again, another example. This is straightforward. We've got a single positive charge here on the potassium, single negative on the chloride. So we only need one of each to balance out, giving a 0 charge for potassium chloride. Calcium, 2+, oxygen, 2 negative. So once again, only one of each required to form calcium oxide, 0 charge there. And another example, so this is when the cation and anion have different charges as they do here. So once again, calcium 2+, but chloride only has a single negative charge, so we need 2 of those to balance the charge on the one calcium. How do we write that? So we started with a 2+ calcium and a negatively charged chloride anion, but the actual compound itself requires 1 calcium but 2 chloride anions to form calcium chloride. All right, to write the formula, place the cation first and then the anion, but omit the charges. So they are just assumed when you're looking at an ionic compound, that you're looking at charged species, charged atoms. Use subscripts to show the number of each ion needed to have a 0 overall charge, and we've done that here with 2 chlorides. And when there's no subscript written, which there are none there, and there are none there, then it's assumed to be 1 atom of each of those elements. All right, now let's move on to naming ionic compounds. So let's start by naming the main group cations. So keep that in mind, main group elements, main group cations. These are just named for the element from which they are formed. All right, so here we have the sodium cation. And this is formed from sodium, so we simply call it sodium. The name doesn't change. The name stays the same. So you can just call it sodium, you can call it sodium cation or sodium ion. All right, same thing applies to potassium. It's a main group cation, so we simply call it potassium or the potassium cation. Calcium cation, magnesium cation. So they're very simple and they take care of some of your tutorial questions. All right, this is where it starts to get a little bit tricky. So who remembers slide 14? What were we looking at on slide 14? So these are not, we weren't looking at main group, or mostly not main group cations. Well, a few, but mostly something else. We were looking at cations on slide 14. Yes, exactly right. We were looking at those cations, or sorry, those elements, particularly the transition metals, that form ions of different charges, of variable charges. Yep. Okay, so remember that you'll have to refer to that table in some of your naming. Okay, so when you're confronted with something like that, for example, one of the transition metals, like ion, which we can see here, Fe, then you need to name it according to this systematic naming system or according to the common naming system. It would be useful if you know both systems because they both are commonly used. All right, so let's look at the systematic naming system. So here we named the ion simply by following the name of the cation with a Roman numeral in parentheses to indicate the charge on that cation. So if you looked back at that table on slide 14, you would see that Fe, ion, can form a 2+ charge, it can form a 3+ charge. All right, so according to the charge, that determines how we name it using the systematic naming system. So we can say ion 2 using Roman numerals in brackets because it has a 2+ charge. For this one here, for this example, we would simply call it ion 3. Why do we have 3 names? 3 names. Oh, yes, because we've got 2 naming systems here and then just the standard naming system. I don't know. That's my answer. I'm not sure why we have 3 naming systems. But yeah, good question. Just to confuse us, maybe. Yeah, look, yeah, I'm really not sure about that. Okay, here we have when is each used? So these two naming systems, you will see both being used. I'm not aware that one system is used for particular circumstances or particular situations, and the other naming system is used for a different set of circumstances. I can tell you that I commonly see both naming systems being used. Yeah, sorry, I can't be more precise than that. All right, so with the common naming system for the same cations, firstly we need to know in this particular case what this Fe actually stands for. In other words, what is the Latin name? The Latin name for ion, and that's written here for you. Fe comes from the name ferrum. So that's the first thing you need to know. Then you need to just determine the lesser charge and the greater charge on the ion. So this example, this cation with the lesser charge is named, the name ferrum is changed to ferrous. So we use the suffix OUS. And then the cation with the higher charge, the 3+, we use the suffix IC. So ferrum becomes ferric. All right, so have a go at both naming systems when you come across one of those metals that form different charges. Just so you're at least familiar with both of them. How do you write the negative? The negative ones, we're not dealing with the negative ones, only the positive ones. All right, so we just looked at ion as an example, Fe2+, Fe3+. Using the systematic naming system, we can call them ion 2 and ion 3. Using the common naming system, ion becomes ferrous and ferric. Here are some other examples. So copper is a good one. Here are the different cations, not the only two, but just the two shown here. Systematic name is copper 1 and copper 2, or cuprous and cupric, because of course that Cu is derived from cuprum, not from copper itself. All right, they're probably the main ones. So remember this table also for at least one or more of your tutorial questions. All right, now let's look at the anions. Anions are also named differently. So you've got to remember this, that when you come across an anion, we name these by replacing the ending of the normal element name with the suffix "ide". In other words, a neutral atom would be called bromine, but a charged atom would be referred to as bromide. Neutral chlorine, but when it's an anion, chlorine becomes chloride. Fluorine neutral, fluoride. When it's charged, iodine, iodide, oxygen, oxide. Remember this one, this will come up quite often. Then we have sulfur and sulfide. All right, so this is also a very useful slide to refer to. All right, so let's look at naming ionic compounds, such as this one here, NaF, or this one here, MgCl2. So we name the cation, name the anion, don't specify the charges. Okay. All right, single sodium, single fluoride, one of each required to form sodium fluoride. That's straightforward. Here we have one magnesium and we have one chloride, but you can see that given that there's only a single negative here, that would not balance the 2+ of the magnesium. So in the actual compound, the ionic compound itself, yes, we still have one magnesium, but we have two chlorides. Okay, so the name is still magnesium chloride. We're not going to say magnesium dichloride, and the reason this is mentioned here is because the use of prefixes such as di and tri and so on, that's how you name covalent compounds, not the ionic compounds that we're looking at tonight. All right, so that's one of the main differences between naming ionic compounds, which is what we're looking at on this slide, and covalent compounds, which we'll tackle next week. All right, so that's quite straightforward there. All right, how to name an ionic compound that contains a metal with a variable charge. So give the name for this ionic compound here. So of course you would have to look up the position of these elements on the periodic table, and if you did that, you would find, of course, Cu copper would belong to that transition metal group that form cations of various charges. All right, determine the charge on the cation. All right, how do we do that? How do we know what charge that's forming? Well, in this case, it's pretty easy because we know that a single chlorine will form a negative charge. There are two of those present in this compound for a total of a two negative charge, which means that this copper cation must have a +2 charge to make the overall charge 0. All right, name the cation and the anion. So of course, because copper is one of those variable charged elements, we can use either the systematic naming system, and that gives us copper 2, or the common naming system, which gives us cupric. And then don't forget with the anion, the end of the name changes to "ide". So chlorine, when it's charged, becomes chloride. All right, write the name of the cation first, then the anion, and the answer is copper 2 chloride or cupric chloride. All right, very briefly now, physical properties of ionic compounds. In the grand scheme of bonding, ionic compounds tend to be pretty tough. Ionic bonds tend to be quite strong bonds. So ionic compounds are solids that have very high melting points and extremely high boiling points. And you can see a great example there. Sodium chloride has a melting point of 800 degrees Celsius, a boiling point over 1400 degrees Celsius. So if you're looking at a list of different compounds, and you need to determine very quickly which one has the highest melting point or which one has the highest boiling point, look for the ionic compound amongst those compounds. All right, if you're looking at an ionic compound versus other compounds which are not ionic, that is, they're not formed between a metal and a non-metal, then you can be quite sure that the ionic compound will have the higher melting point and higher boiling point. Okay, so when ionic compounds are dissolved in water, they will separate into their respective cations and anions that formed that compound in the first place. This is called dissociation. And we can see that happening here with sodium chloride when it's dissolved in water. The sodium ions dissociate from the chloride ions, and this resulting solution will conduct an electrical current. All right, so that's all we'll say now about physical properties. All right, and our final slide. Now here we have some excellent examples of ions, but unlike the ionic compounds that we've been looking at in this lecture, this is a different class of ions, and they're called polyatomic ions. So you clearly see why they're ions, because they are charged. These are charged molecules, all charged molecules. So what differentiates these ions, these polyatomic ions, from the ionic compounds that we've looked at? So the difference between these ions and something like sodium chloride, for example. Sodium chloride is an ionic compound. The main difference is that the atoms in these compounds here are not bonded together using ionic bonds. They are bonded together using a different type of bond called covalent bonding, which once again we'll look at next week. So these are actually covalent compounds that carry overall charges because, of course, the number of protons and electrons are unequal. All right, having said that, some of these are very, very important for different groups of students depending on your major. So when it comes to students that are studying animals, then these two become very important, carbonate or bicarbonate. This one is a good one to remember just for the purpose of one of your early tutorial questions. So keep this one in mind, CO3 2-. You'll see it again. And this is the carbonate polyatomic ion. Cyanide, we'll come back to that one next week as a good example of a covalent compound. All right, these two here are really important for everyone, particularly anyone studying plants. Okay, here we have the nitrate polyatomic ion and the nitrite. Okay, who can tell me which of these two, anyone that's studying plants, which of these two is very important as a nitrogen source for plants? Nitrate, correct, nitrate. So plants do like nitrate. They can actually take up nitrate. Okay, what about nitrite? Do plants like nitrite? No, they don't. It's actually toxic. Nitrite is actually toxic, and there's reasons for that, physiological reasons, which you will discover when you go on to do plant physiology. But anyway, let's look at the difference between these two polyatomic ions. What is the difference between them, between nitrate and nitrite? Have a close look and tell me what the difference is. They're both negatively charged. They both carry a single negative charge. Oxygen, correct. So look at nitrate. It has 3 oxygen atoms. Nitrite has 2 oxygen atoms. Okay, so the difference between these two actually determines the difference in the name. Okay, nitrate versus nitrite. Okay, ate or ite. Okay, so this one with fewer oxygens, we use ite. This example here with the 3 oxygens, it has 1 additional oxygen, so we use ate. Okay, nitrate versus nitrite. And the same rule applies to these polyatomic ions of sulfur. So this one here, have a look at sulfate and sulfite. Okay, same rule applies there. 3 oxygens here, 4 oxygens there, and that determines the suffix that's used in the name, sulfate versus sulfite. Okay, so these two really important for most students. This one here, hydroxide. We're going to talk a lot about the hydroxide, polyatomic ion. Phosphate, very important. We'll talk a lot about phosphate also. All right, so that completes our, oh, that was a very quick lecture. Very quick. Okay. It's always faster online for some reason. All right, here are your tutorial questions based on tonight's lecture. Keep in mind that these questions are not assessed. Okay, these 2 questions are not assessed. That is, they're not assessed as far as the online quiz goes. So by all means, use the online quiz to check your answers. The online quiz for the non-assessed tutorial questions, they don't close for the entire semester. Okay, they stay open until your exams are finished, your final exams are finished. All right, but certainly work your way through, because the tutorial questions are very important in terms of revising, making sure that you're understanding certain concepts. And of course, some of the tutorial questions may come up again in some way, in some shape or form. They may come up again in either your mid-semester test or in your final exam. So even these non-assessed ones are really, really important to do at some stage. And I do understand that once you really get into semester, those assignments that are assessed take over. They become your priority, and that's fair enough. So what many students do, they start, they work through these questions, but they don't tackle the actual online quiz until they're doing their preparation for exams, for example. All right, now keep in mind that this set of questions includes both tonight's ionic compounds, and then you'll also see a second part in tutorial 3 that tackles covalent compounds. Leave these questions until we've completed our lecture next week. Okay. All right, so that's it for tonight. Does anyone have any questions? Any questions at all?
Hello.
Hello,
It's
yes.
Simon. I have a question in regards to, in the middle of your lecture, you were talking about the columns on the periodic table 1.
Yes, the group numbers, yes.
I didn't quite comprehend how you could deduce the actual
charge, the actual charge.
Yeah, exactly.
Okay, all right, let's go back to that. All right, here we go. All right, so this is probably the main slide you should look at.
Yes.
Excuse me. All right, so here's the group number, group 1A.
Yes.
So these metals in group 1A, they form a +1 charge. Okay, so that relates to the number that you find in the group number.
Right.
Okay, group 1A, +1 charge. All right, here we have the metals in group 2A.
Yeah.
They also form positive charges. So here's the relationship between the group number, so 2A, and the size of the charge, 2+. There's the relationship right there.
Right.
Okay, and we can apply that, sorry, not that same rule, a different rule to these elements here, group 7A and group 6A. So let's look at group 6A to work out the charge. So these all form, commonly form anions, the negative charges. Yep. Right, so to work out the size of the charge for group 6A, we simply say 8 take away 6.
Is it always 8?
Yep, always 8. 8 take away 6. That leaves us with 2, so 2 negative charge. Okay. Same applies to the group 7A halogens. Okay, they also form negative charges. Yeah. To work out the size of those charges, that is the magnitude of the charge, you simply say 8, always say 8, take away 7 equals 1, and hence we have a single -1 charge on these elements.
Understood, yeah.
Okay, does that make more sense?
Yes, absolutely.
Excellent, excellent. Are there any more questions?
I have another question, but I'm not too sure how to describe. Maybe you'll be able to predict what I'm trying to say here. But
all right,
with the ionic compound, where you've got 2 different elements.
Yes.
And then we had to derive
the name.
Not the name, the actual charge, and how you swap the charge juxtaposed from one element from one side and the other to the other side.
Right. So something like this.
For example, yes, that's
something
correct.
like this. Yeah. Yeah.
correct.
All right, okay. So for this example, all right, so we'll look at calcium. And actually, instead of doing that, let me just go back. All right, so let's find calcium first on the periodic table. Even though it's actually written there, it doesn't matter.
Yep.
Let's find calcium. Here it is here.
Yep.
Calcium's here, group 2A.
Yes.
Yep, it's a metal, so it forms a positive charge.
That's correct.
Group 2A, so it forms a 2+ charge.
Yes.
Okay, now let's look at, oh, I should have looked at this first. What's the other example? Here. So here we've got fluorine, for example. Let's check fluorine.
Is it fluoride or fluorine?
Fluoride. Fluoride, because it's charged, we say fluoride. That's correct. Okay, so fluorine's found here on the periodic table. But because it's charged, we call it fluoride, which you're right.
Yeah.
We know that it forms a negative charge
Yes.
because it's a non-metal.
Yes.
And we know the magnitude of that charge because it belongs to group 7A. In other words, 8 take away 7 equals 1. So it's a single negative on the fluoride.
Okay.
Okay. So if we go back here,
Yes.
so that's how you determine the charges. Easy way of determining the charges. So we have only a single negative charge here.
Yes.
But we have a 2+ charge here.
Yes.
Yeah. So if we were to bond these together, if these were to bond together, it wouldn't be balanced, would it?
So is that another way of saying it wouldn't be neutral? Is that what you're saying?
That's right. It would not be neutral. It would not give you an overall or a net charge of 0.
Exactly.
Yeah. The compound, the final compound that forms would not have a 0 overall charge.
Okay.
Okay, so that's why you tend to find two fluoride atoms, which is actually illustrated here, 2 fluoride atoms bonded to every 1 calcium cation.
Understood.
Yeah?
Yeah.
I don't know if you can't really see that very well here, illustrated here, but that certainly explains why this is the formula for calcium fluoride. 1 calcium, 2 fluorides. Yep. To gain that 0 overall charge on the compound. Yeah, does that make more sense?
Yes, it does.
Excellent.
And the last question I have, and I promise it's the last
No,
question.
that's all right. Questions are great.
Towards the end, the last page, where you had the
the polyatomic ions.
Yes, you had hydroxide.
Yes.
So how come it's ide?
Why is it ide? Oh, because oxygen. When oxygen forms one of these ions, one of these polyatomic ions, it's referred to as oxide.
But did you not say that it's 8 or 8, or is that something else?
Yeah, that's when you have, that's something else.
Okay.
Yeah. So that's when you have these very, very similar polyatomic ions that essentially differ by 1 oxygen.
Right. So with hydroxide.
So, for example, nitrate and nitrite, or sulfate and sulfite.
Okay. So with hydroxide, it is what it is.
It is what it is. Yeah. The name is actually fairly descriptive in that the hydra comes from the hydrogen that you can see there, and the oxide is used to describe the oxygen. And I think that maybe, let's go back for a second. Oh, here it is. And we also can see here in this table that oxygen in its charged state is referred to as oxide.
Okay.
Yeah. Okay. Along with the other ides.
Anion. Yeah, exactly.
Yeah. Sometimes you're right. It just is what it is.
Yeah.
And there are probably reasons for that. There could be historical reasons that I'm not aware of, but that's certainly the way that we describe this particular species here as hydroxide.
Thank
Yeah,
you, Doctor.
good questions. You're welcome anytime.
Is this true that the Russian scientist Mendeleev had a dream of the periodic table?
It's true, apparently. So
Yeah,
I hear. So I read
yeah, I
about
read the book.
Mendeley. Did you read that? Have you
Yeah,
seen the video, the YouTube
no,
video?
but I read the book and I can't believe he had that kind of.
Ah, it's just amazing. It really is amazing. If
It is
anyone gets
amazing.
a chance before semester really heats up, have a look for a YouTube video
Yep.
on how the periodic table was first assembled. It's really quite amazing.
Okay.
Quite amazing. The brilliance of certain people
Yeah.
to basically predict what elements would fill the gaps in the periodic table.
Yeah.
Really amazing stuff.
It was
It really
almost like
is.
a
Yeah.
premonition, more or less.
Yeah, absolutely. Absolutely.
Thank you, Doctor.
Yeah, really interesting. You're welcome. You're welcome anytime. All right. Thank you, everyone, for coming along. We ended up with a good sized class tonight, which is great. And is there anyone, I might actually stop the recording so that you can be free to speak. Right, recording, stop.